Hello students, welcome to the video lectures of speech and natural language processing. The agenda of today's class is we'll discuss about detecting and correcting spelling errors, followed by minimum edit distance. So when I say minimum edit distance, we talk about 11 stems distance, which uses dynamic programming, and we'll see that with an example as well. So first one is detecting and correcting spelling errors. It's a vital aspect of NLP. This significantly will impact the performance of NLP applications, including search engines, chatbots, and text analysis systems. So spell checking is crucial for the following reasons. First thing is it improves the communication. So how it improves the communication is correct spelling will always ensure the clarity and understanding. That's how our written communication will be more effective. Second is enhances the user experience. So your search engines and text editors, which provide you automatic spelling corrections, are the better example to illustrate about enhancing the user experience. Next is increases the data quality. When you have a very good input, I mean to say, when you have a cleaned and processed data without any spelling errors, which is fed to a model, the model will really work accurately and ensures there won't be any kind of errors. That is how it increases the data quality. Then we shall look into the common techniques for spell checking. So first one is dictionary based. So this is somehow called as the simplest method. Dictionary based approach is nothing but you'll maintain a corpora or you'll maintain a database of the words with correct spelling. And if whenever a word is encountered, it just goes to the database and checks whether the match exists or not. And if there is a match, then it just checks whether the spelling is correct or not in the dictionary. And this is said to be simple and very fast. Next one is phonetic algorithms. So phonetic algorithms, what this generally does is, it just converts the given word into phonetic representation. So why it has to do that is, so there are a couple of words which have different spellings but might pronounce same. I mean, the sound of the word will be same, but only the difference would be in the spelling. For example, if I write, uh, you know, mm, Smith, so both have different spelling, but the pronunciation will be same. Then we talk about edit distance algorithms. So edit distance is nothing but it is the minimum number of operations that are required to convert one string to the other string. So when I say minimum number of operations, we'll see what operation exists in this edit distance algorithm. So it's the minimum number of operations required to transform one string into other. The most common operations are insertion, deletion, and substitution of the characters. So string 1 be the source string and string 2 be the target string. So the minimum edit distance measures how far one string is from the other in terms of necessary edits. So these are various examples what you can see right now. So for insertion operation, see, so we have to transform character CA to CAT. This means we have to insert this alphabet A. Understand? So this is called insertion operation. Now you are just trying to make string cat to be converted into CA. So how we can do this? By removing this extra alphabet T. So that is what deleting operation is. Then substitution operation. Now we have to transform the string cat to bat. So what we have to do? Just we have to replace this C with B. So that is what substituting is. C with B. It becomes bat. So minimum edit distance, as I told you, when we talk about minimum edit distance, we discuss about Levenshtein's distance algorithm. And so it uses dynamic programming to build a matrix where each cell represents the minimum number of edits required to transform substrings of the source into the target. So what we do is we initialize a 2D matrix. So the first string, the string one, that is a source string and a target string, that is the transformation of one string to the other string that happens will be taken into the matrix, one in a row, one in another column. And we perform the insertion, deletion, or substitution operations to transform it. So recurrence relation states that for each character in both strings, compute the cost of substitution, insertion, and deletion. Select the operation that gives the minimum cost. So if the character matches, then there is no cost. If the character does not match, so apply the minimum of the three operations, that is insertion, deletion, or substitution. Now let us try to understand this with an example. So here I'm just trying to show you two strings which are there. That is, one is sitting, the other one is kitten. So what is this we are trying to do in this particular diagram is I'm just trying to transform the string kitten to sitting. Okay. So these two are nothing but you can consider them as null. This and this as null. So now imagine before we start and explain you all these numbers, what are these numbers and etc. Let me tell you a couple of rules that exist. So basically, in this diagram, a vertical arrow will tell you as an insertion operation, and a horizontal arrow will represent you remove. then there are two conditions in this particular 11 tens distance. So that is when row not equal to column. When I say this, just remember when the alphabet but that is present anywhere in this, okay, is not equal to the alphabet which is present here. That means when row is not equal to column, what is the basic operation that we need to do and how come this number have arrived is the logic behind this. So now just imagine we have um, this is replace, this is remove, and this is insert. Okay. So now what you have to do is if row is not equal to column, when I say row not equal to column, what you're trying to transform the particular given string, when those two alphabet doesn't match, what you have to do is you have to consider the minimum of these three, that is the minimum of remove, replace or insert, and you have to do +1 for that. This you have to write as an output in this particular area. Next condition is if row is equal to column, then what you have to do is you have to simply, you just have to simply consider the diagonal value. The, again, this is replace, this is insert, right? You just have to copy the diagonal value which is present over here to this area. Understood? So that is when row is equal to column and row not is equal to column. These are the two conditions which you have to do. And then now you can see here, for example, now I want to transform this null to S. What I have to do, sorry, for first, let us say I want to transform null to null. So when I want to do this operation, I need not do any other insertion or removal or replace operation. So that's the reason why I took 0 here. So minimum operations I need are 0 because both characters are matching. Then I am doing this null compared with yes. So what I have to do when null is compared with yes, yes. So when null is compared with yes, I have to insert the alphabet or string called yes. So the minimum operation required is insertion, that is 1. Got it? So then I, now null is being compared with I. So what do we have to do? So when we reach this particular area, so null should be replaced with these two alphabets, that is yes and I. So earlier it was yes, now we are trying to add I to it. So we have to add two strings to make it convert to S and I. That is transformation of null into Si. So the minimum operation required are insertion of two strings, that is S and I, that is number 2. Then we come to T. So null has to be now transformed into S, I and T, right? So now earlier it was Si, we add T to it, so it becomes 3, right? So that's what is written here. Similarly, compare null with T, just add another T here. So we have to insert 4 strings or 4 alphabets. That's why we have taken 4. Then 5, 6, 7, and so on. That is SITTING. This is what is the string which is replaced now. So to transform null into sitting, these are the minimum operations what we need. Hope you got it. So you might have a question. So I told you if row is not equal to column, we have to consider a minimum of these 3 and just add 1 to it, right? So I'll explain you any one point now here. Yes, consider this 3. Now K is being compared with T here, right? Just I'll draw a line. So K is being compared with 3 T. So now the minimum of, one second. Yeah. So K is being compared with T. Now, how did we arrive the value 3 here is? So consider the minimum of these 3 numbers. So minimum of these 3 is 2. So just add +1 to it. So that's how it became 3. Okay. And you can also check in this way. So when K has to be replaced with sit. So these are the 3 alphabets which has to be added, right? So that is 1, 2, 3. 3 insertion has to take place. That's the reason we have taken 3 here. In any of the form you can imagine. Then I would like to also tell you about these things. Well, comparison of T with this T. Okay. Now you can see you are observing a number called 1 here. Why? Because the condition what I mentioned is if row is equal to column, so you have to just replace the diagonal value, right? So that is what we have done here. So the diagonal value is 1. We are just replacing it with 1. Got it? Right. So this is how you need to calculate the Levenshtein distance, and the minimum edit distance of this particular sitting to kitten is 3. Hope you understood, students. So what are the applications of this minimum edit distance? So there is spell checkers, speech recognition, machine translation, plagiarism detection, DNA sequence alignment. These are all the applications. Thank you.